Okay, so we talked about the example study from that we worked with on ERCOT a little bit. Um, the study challenges related to working with these load models are, it's really hard to get this data for the load profiles as well as the synchronous machine information. A little bit about some of the other associated things that you might run into with large loads. This one, so flicker. As we know, we can, when we have fast voltage fluctuations that can result in problematic flicker levels, and we have standards which are, give us basically what's allowable in terms of flicker. To assess this, you may need an EMT simulation. You could also get a feel for this using power flow tools by just applying the the difference, like your max power and your min power, and seeing how much the voltage changes. Yeah, I might have to make some assumptions around what sort of voltage control, what the voltage controllers in the area are doing, but you can get an idea of that from your power flow tools as well. But if you want to look at it in detail, you may need to do this EMT if you think it's going to be a problem. Yeah, in quantifying it in EMT, you typically will have some simulated flicker meters in the EMT tool as well. And in order to do this, you're going to need synchronous machine shaft models. And a range of load profiles and measurements are useful as well. And I would say just like probably from what we're seeing so far, the power, like the impact on generator torsionals is going to be more restrictive than the flicker issue. But, that'll change system to system as well. Okay, so what about harmonics? So we've touched on it a couple times, but we have seen some events of some fairly substantial harmonics associated with data centers, and we can study this. What we need to do is we need the load vendors to go take their devices and put them in a test bench and do a sort of perturbation analysis on it to tell us the harmonic impedance and the harmonic current injection of those power electronics, which is something they can do in a lab. It's a little bit complicated, but we have got that sort of data for at least one facility. And once you have that equivalent harmonic source, you can put it in a harmonic power flow solution, which gives you the harmonic voltage profiles around the system. And you can do this kind of like over a wide range of system conditions as well. And so, yeah, there's very useful studies you could do on this side of things. Generally, this is not something you need to do in EMT, and EMT may not even be the best program to do it because these harmonic power flow programs they handle this type of data much more efficiently than EMT would, and I don't think you can get this Norton equivalent into EMT the way not the same way that you can handle it in the harmonic power flow tools at least. So there's basically like tools that are designed for this to study this harmonic impact, and your EMT tool may not be the one to give you may give you an answer, but you may need to add a lot more detail in it, and it's not going to have a harmonic power flow calculating mechanism in it, so it's not always the right tool to look at harmonics in. So we can also have an impact on machine mode oscillations and inter-area oscillations. And typically here we would suggest folks would just use phasor domain tools to study this at key machine or system modes. So we know that the phasor domain models are pretty good at representing these machine mode and inter-area mode oscillations. So in terms of data, transit stability models for the load with flexible load profiles, you can just push that load to perturb at a machine mode or at an area mode and see what impact that has on the system. And it's not what we're not changing the, let's say, the stability of that mode necessarily. We are repeatedly exciting it when we can see what sort of impact that might have on nearby machines, but we're not changing the damping of that mode by doing that, because again, this is a forced oscillation. It's not a damping based oscillation. Okay, so in terms of ride-through problem, small voltage depressions may lead to load disconnections. So the UPS trigger thresholds can be very sensitive. For this example here, something like 0.8 per unit might cause the load to move on to UPS and disconnect from the system. And for the load, this is totally fine, but for the system, this is not great. This basically looks like the load has disappeared for a while and then come back. And this, it can come back at different time frames. We don't know necessarily how fast it's going to come back after it goes to UPS, but this is something that they could probably tell you. And maybe they can come back, let's say it goes on to UPS, and then if the voltage looks really good shortly after, they might be able to bring it back pretty quick, maybe on a ramp rate or maybe all at once, kind of depending what the system needs. So that is somewhat configurable inside the UPS. So yeah, when the type of issues that we might be worried about when it comes to the ride-through impact, one is of course the load rejection, temporary overvoltage. So even if we are, in this previous example where we trip where the load goes onto UPS, this voltage might go quite high when this load is gone, because you have a load rejection happening, and that load rejection it might be quite large, and it might cause things to trip if it's big enough. And specifically, you want to be thinking about SATCOMs. If you have a SATCOM there, that's there to mitigate the temporary overvoltage. And if your overvoltage goes beyond what the SATCOM can handle and causes the SATCOM to disconnect, then it's going to get even higher once the SATCOM trips, right? So you want to study that pretty carefully and make sure it's within the trip limits of nearby devices. It might cause problems with VAR adequacy or dynamic voltage problems, and it might have an impact on the frequency of the grid, depending on what sort of system you're in. For smaller inertia systems, having a big data center could disconnect very, very quickly. Will definitely cause an over frequency that might be problematic. It might impact the generator resource commitment or create dispatching problems as well once we lose a whole bunch of load like that. The study tools to assess this are going to be mostly a mix of phasor domain and EMT tools. And there may be some special data required from the load, which is the ride-through characteristics of the load and the ride-through characteristics of nearby devices on the system. So, thinking about dynamic VARs a little bit and these load fluctuations, when we see the load go, let's say it has a big downswing and then comes up again, and when the power goes down, the capacitor banks are probably going to switch out because the voltage will be pretty high probably. But the capacitor banks have a time constant before they can come back in typically. So there might be a time where the load comes back in and the caps are still out, and then your overvoltage problem might have turned into an undervoltage problem pretty quickly. So that's something to just to be aware of in terms of the dynamic bars. And there's a bit of a sidebar on other reasons that switch caps are bad, I guess. One, of course, that switching caps causes transients on systems, and the other thing it does, it can weaken the system by increasing the 60 hertz impedance of the network. When you have more capacitance in the system, you're taking the parallel resonances and you're shifting them to lower frequencies. So then your impedances will all go up as a result of that cap being in. So it'll increase voltage sensitivity and all these things. And the increased likelihood of problematic harmonic resonances in the system. They are, I guess, the other thing that's not here, but capacitor banks, the reactive output is extremely limited by the voltage. Obviously, you don't get a lot of bars out of the cap when the voltage goes down. The StatCom basically solves all these issues in a lot of ways, but they require more time and more money. So there's a trade-off there between StatComs and capacitors.
Is another approach to maybe solving this issue as you've presented it would be to slow down their reconnect frame rate after tripping. To basically say if you disconnect for whatever reason, you can only reconnect over such frame rate.
Yeah, that can definitely be a solution.
The SBC or StatCom's just so expensive.
Yeah.
Yeah, and there's a lot of resistance to them.
Yeah, I mean, it kind of depends on what the specific problem is. If it's frequency, then probably want to come back up as soon as possible. But if your system can handle it, and coming back slow is probably going to be better. Yeah, and then just another note on the damping studies. So we know SSC and SSTI are dependent on the amount of damping that we get from power electronics. If damping becomes negative at a resonance point, whether it's electrical or mechanical, we can get instability. And again, this is separate from the discussion around forced oscillation. And we need to do detailed studies in EMT to suss this out. And if we want to do that study, we have to get the dynamic impedance characteristics of the load and the dynamic model of the grid as well. The other thing that I guess as an alternative to this is if you take the loads and you take the UPSs and the power supplies and you just in a test bench, like in a lab somewhere, if you can kind of prove that the damping is positive and that they're not bringing negative damping to the system, then maybe you can have some assurance that this won't happen on the system when you connect these things. And maybe you don't, that specific aspect maybe can be mitigated somewhat. But as we kind of mentioned, the SSCI issue can be impacted by more than just damping. You might connect one of these loads, and even though it has a perfectly fine damping profile, it might shift the resonance of the surrounding system such that you're now have moved it to an unstable frequency range. So if you have a complicated series compensated system with multiple IBRs that maybe are marginally stable, then you'll definitely want to try to get the detailed model if you in order to assess the damping of the network. Okay, so what kind of models do you need, right? This is the big question. How do we study this stuff, and what kind of models do you need? So one type of EMT model is not equal to another type of EMT model for this sort of thing, and the same thing with phase domain, right? There's some things we can study without having these sort of ultra detailed models that we that are OEM provided and all these things, depending on the sort of risk that we're looking at. So this is This is this monstrous table that Andrew made. I'm going to blame it on him. And it's kind of, it kind of hurts your brain to look at. But we can look at it sort of just, I'd say just we'll pick a couple rows that are sort of useful for the conversation here, and we'll drive a couple points home. And we're not going to talk about everything here. It's too much. So a few ones here. The first one, SSTI screening. So an SSTI here might not even be the right word. I mean, SSTI due to software cycling, right? So due to forced oscillation. Probably we should say something forced oscillation related and not SSTI, but I guess that's just the language we're choosing here. So screening, we can do this with just a power flow model for the software cycling issue. And if we want to diagnose the software cycling issue, we can use a EMT model with the software cycling component, which doesn't have to, that can be OEM agnostic. So we, as I mentioned, we just, in our tests so far, we've just been using just a resistor, variable resistor basically, and we're playing in certain profiles. And that's probably going to be good enough to assess the software cycling impact. So you don't necessarily need this EMT model, including grid-facing control representation. That's OEM specific for that specific item. Torque impact due to fast changes in load. So if you want to assess, aside from the actual like oscillations, every time you have a big change in power from a load, that'll like kind of, that's a big phase angle step, and it there'll be some of that phase angle shift that sort of makes its way through to the generators. And even if it doesn't, even if it's not happening at a certain frequency or anything like that, just having a lot of big load steps in the system, even if they're not lining up with a certain frequency component, they can still have some impact. So, so that's what that row is for. And again, that's basically same as the software cycling item there. So the next two, SSTA and SSCI, due to control damping. Again, if we want to have those, then if we want to study that, then we need those EMT models, which have the grid-facing control representation, which would be OEM specific. Harmonic model creation, you can do this in, you can use EMT to create the harmonic model that I talked about, that Norton equivalent. You can do that in EMT if you want. To actually do the study, we'd say OEM specific harmonic model, that Norton source is what you really need for the harmonic study. You might be able to do it with some other tools as well. Collector evaluation, power flow model, and possibly EMT. Fault ride through sensitivity. So this one is where we would say, so that's, it's a really good point. So if we want to look at the, if we want to study the ride through capability, ride through impact, let's say, on the system, this first one, ride through sensitivity. So how sensitive the load is going to be to events on the system. There's a EMT model with protection, that's OEM specific, and then EMT model with grid facing control representation. The difference between these two is probably the EMT model with protection. If it's a strong system, then maybe the controls won't make necessarily as much of an impact. If it's a weak system, then you need the protections and you need the control as well, because there might be an impact that the controller would be having. Right through impact on the system, if you have a given event and whether the load would trip for that, you may, again, it's kind of similar to the previous one. You can figure out what sort of impact that would have. Possibly you don't need the models for that one if you know the characteristic ride through. Frequency impact, if you know the ride through characteristic, then you probably don't necessarily need the EMT model. You can assess that through just knowing the protection information, likely. And then I think these other ones, machine wood oscillations, inner area, and resource balancing, steady state constraints and dynamic bars. We kind of touched on all of those, and those ones we basically are not needing EMT models for. Those are all sort of power flow or transient stability. So that's, yeah, so I don't know. Hopefully that helps you a little bit with this table here. If you have some more questions, I will direct you to Andrew. It's his fault. So, all right, so let's talk a little bit about different requirements that you might use to limit the sort of detrimental effects that the load characteristics have. So the first one here would be individual requirements. So basically, you get the load, you talk to the load, they tell you what sort of fluctuations they're going to output, whatever they can tell you. They're going to give you their ride-through characteristics and their damping, etc. And then you do a very detailed study and try to figure out, try to assess the impact that the load is going to have on nearby generation or on your system. And that study can be quite challenging. You might not even have enough data to really get the answers that you're looking for in that study, but you can do it. And assuming you have the right input data, which we already talked about, is going to be a challenge. The sort of like potential issue is that you might figure out that there's no there's no impact on nearby machines, but you've potentially now just because there's no impact, for one thing, it doesn't mean that, okay, when the next load comes along now, it's going to probably have an impact. So you might have sort of taken all the margin out of the system just with that load, with that first load connecting, which might be a problem. The second option here is to have a blanket requirement that you can say, let's say 25 megawatts or something like that. If you're going to be fluctuating more than 25 megawatts or some other ramp rate, then you need a detailed study. If you're under that, then maybe you'll pass through without a detailed study. And the third one would be just a blanket requirement to say, apply some conservative requirement to all loads and just say that no detailed studies are needed at all. So the problem there is trying to figure out that threshold might be challenging. If you make the threshold too small, perhaps none of the loads will be able to connect, and maybe that's not your problem, which is fine. But if you make that threshold too big, then you might, at the end of the day, have some damage to system equipment or nearby generators, and they might come back at you and say, why did you let the loads fluctuate this much when you didn't maybe do due diligence with studies along the way? So there's pros and cons to these various approaches, and we're seeing people kind of doing different things. Went through all of these. So a few variations on what kind of requirements you can use specifically on the active power variations. Really, there's the first one here is to say to the load that we know we have some machines in the system that have torsional modes at 10 hertz and 15 hertz. So we need the load to stay less than a certain harmonic content level at those frequencies. And the loads are going to be generally pretty happy with this. They from at least my experience, they're able to fluctuate a lot at levels at a harmonic content that isn't going to impact the nearby machines, and the harmonic contact exactly that's lining up very close to The synchronous machine is probably going to be pretty small. So this is probably the ones that the load would like to do. There are a few kind of potential downsides here. It requires very special, careful specification of that frequency content measurement. We have to say, maybe using an FFT or some sort of, probably an FFT, and we have to sort of bin it in certain frequency groups, and that's sort of that can have some, we can have some nuances there. It may be, you have to kind of understand how the frequencies are going to interplay with each other, right? So if you have some harmonic content at one sort of certain frequency and then at another frequency, and when it changes from one to another, what does that do across the frequency spectrum? So it'll be a little bit more difficult to sort of determine whether there can be some complexities there. Duration of perturbation interacts with magnitude of perturbation. Again, these are things that we don't really know exactly how they're going to look in the actual loads. But assuming if you have one of these requirements, you would have to have some sort of requirement that says, okay, you can't fluctuate, you can't have more than 1 megawatt at 10 hertz for some certain amount of time as well. So it's probably going to be a time sensitivity there as well, and we don't exactly know what to put there yet. And it may be difficult to monitor and enforce, and may be difficult to conceptualize compared to some other methods. And also, you might just have data center loads that they might not be able to avoid certain frequencies. Again, this is not necessarily your problem if you're setting the requirement. And another alternative here, or framework alternative, is to just set an absolute limit on the magnitude of the variation. So, for example, here you could set a variation limit of 25 megawatts and 5 seconds, and basically then you can just draw a box like this and move it around on the load profile. And if the variation ever goes outside the bounds of the box, to the top or bottom, then they are not meeting the variation criteria. So it's kind of easier to understand, easier to enforce, but the loads may not be as happy with you because it's more restrictive on the total output, and it's a little bit less nuanced and potentially more limiting on them compared to the other option. And it might be difficult to come up with this 25 megawatt number. And on the ride-through side, how do we come up with criteria there? So you can use similar to IBR fault ride-through curve. So a lot of folks have been using things like PRC29 curves as a baseline. The question, there's some other details we have to think about there. Like, does this mean no trip or no temporary reduction? If you are allowing a temporary reduction, how fast do they need to return, and at what sort of ramp rate? And we, considering all those things we talked about, load rejection, over voltage, frequency, etc., may influence that decision. If we have a big, several data centers may be located close to each other and they all trip for something, this could, or the temporary disconnect that might cause a large, significant overvoltage, and we might struggle with how to fix that. Maybe we can use StatComs, but it might need a lot of StatComs to fix it. So yeah, in the meantime, the loads may not be able to meet this criteria. As I kind of mentioned, these loads are kind of where IBRs were maybe like 15 years ago or something. So they don't have really any ride-through capability at the load level. They're working to fix that. But just so folks kind of if you set a very strict criteria, right now the capability to meet that is not really out there. The other sort of thing that isn't mentioned here is that you can also, you can also fix this with a really big battery as well, basically have the battery monitor whether the load is, if it trips, it basically just starts absorbing a lot of active power to make it look like, from the grid perspective that, the net power didn't change or didn't change for very long sort of thing. So there's some things you can do to sort of patch over this ride-through issue, but they're expensive. And it may take a lot of time to procure.
If you were to design the curve from scratch, not considering the IBR curve, what would you want to consider in that framework? You come up with the different points.
The points on the ride-through curves?
Yeah.
Did
I mean, you can start with the IBR curves, but like there's got to be some sort of theoretical grounding at the end of the day, I feel like.
Yeah, I mean, like the IBR curves came out of, a consensus of the planners and the manufacturers, right? In this case, it's a little bit different because there are UPSs that involved. There are batteries that you can use to sort of fix it a little bit as well. But it's a really good question. I mean, I think the IBR requirements are a decent place to start. In lieu of other information, it seems like the planners are happy with the ride-through capability that they get from like a PRC 29 curve. So might be where we go, but it's a good question. I think it's one that a lot of people, a lot smarter than me, are probably more qualified to answer.
Just to add to Lucas's point, the place to start is talking to the manufacturers and seeing what they can do and seeing if that's good enough. And if it's not good enough in the system, ask for more, and then you'll get it in the future. That's basically what 2800 did. Was that had all the major manufacturers in there, and we would propose protection settings. They'd say no, we can't do that, or they'd say yes, we can. And we got to a place where we were maximizing as much as we could protection settings, but some of those were outside of some of the major manufacturers' range at the time. Then we said, hey, it's 2020. We're going to publish it in 2 years. It's probably another 2 years for implementation. And then they would say, oh, well, we could probably change those in 4 years. So it really starts with starting with something from another technology could help for framing the discussion. But you really have to have that same process of having the iteration between planners and actual equipment. Because on the NERC side, the NERC has always been saying maximize the ride-through, right? And you can't prove max because you can't prove a negative, right? But you can kind of collaborate on saying what's max. And then once you have that, then you got to talk about the supplementary equipment, right?
So I guess, I get that you want the manufacturer to be able to meet the capability. You don't want to design something that's impossible to meet, but I should be able to put that aside for a moment and think about purely from the grid perspective and the physics of the power system. There is a ride-through curve, and it's probably more of like a probability where if I have X curve, the probability of the loss of load or the resource is a certain amount, and what is that magical probability number that you are okay with? But at least the thought in my head is I should be able to design an ideal ride-through curve from the grid perspective. Now, can people meet it's a different question, but that would be like the end goal. And I guess my question that I've thought about is, if you were to design that curve, the ideal grid perspective, how would you do that? And it's going to depend on the system and stuff like that. So more of a framework than saying it should be this number.
I mean, that's a really good question, right? Can you determine what's good from the system side only? Is a really good question. I probably right now, right, the current paradigm with the amount of synchronous machines on the system is anything more than PRC24. This is my opinion before I say the next thing. Anything more than PRC24, which is the synchronous machine ride through, does it matter? If we have a grid event and all the synchronous machines are tripping offline, is there going to be a system left to ride through for the IVRs is like, so in the current paradigm, that's probably the max, right? So they can ride through the most of it. The problem is like for frequency ride through, it's a little bit easier because you can kind of link frequency ride through the under frequency load shedding and loss of load expectations and all that type of thing. For voltage, it's really much more complex to figure out what maximum is. And it's going to change, right? So like the system operators know how often their grid fluctuates or like the maximum and minimum voltages they'll see on the system. And they can do probabilities and figure that out too. But it's probably easier to just ask for as much as you can and point to the reasons why we need ride through and have that. It's probably easier to have that collaborative discussion than have try to optimize your own system based on probabilities. But right now, I mean, the IVR ride through to base 29, actually 2000, they're well outside the synchronous machine trip setting. So that is a great place to start, and it probably gives us margin until we're at like, I don't know, 70+% in penetration all the time of IVRs. Random number I picked. So you certainly could, but is it worth it? Do you get more benefit just having the collaborative discussion? The problem is getting the people in the room to talk about it.
No, because one of the issues is people say, wait, you have a right to curve. How did you justify this?
Yeah.
Oh, I copied it from this other curve is. Maybe it makes sense, but it's not a great answer, in my opinion, to start with.
Well, that was one of the, and you can go read the transcript of the NERC's technical conference on PRC 29 when, so for those who weren't following it, there was a time where there was really, really stringent frequency ride through requirements in PRC 29 that essentially no machines could meet. And basically none of the auxiliary equipment could meet. So part of the justification was I took all of the major disturbances that have happened so far, including the 2 winter storms, plotted all of their frequency excursions maximum against the ride-through curves, and they were not even close. So that was just to show that to go outside of what we have now for frequency, or 2000 for frequency, it made no sense and wasn't justified. And then we ended up moving those in part of the final standard, right? So you can try to show that and say like this makes no sense at all. But on the 2000 side, the manufacturers agreed to do it for IVRs anyway. So it could go both ways, right? Having it be exactly at the optimal piece of the needs of the power system could hamper future development, but they also could go vice versa. So I guess that was a lot of information with no firm answer to your question, but it is really putting those things into standards requirements in regulatory work is wild for a lot of other reasons. And a lot of times the optimal solution isn't what gets into the standard.
Yeah, well, I guess it's similar to that, like, but even beyond ride-through requirements, I can think of other conditions where a load would drop offline suddenly for non-disturbed, like because of market forces or whatever, right? So, for example, if there's 2 data centers that are owned by company A, one's at ERCOT, one's at SPP, and then the prices suddenly swap over to where it's $2 cheaper per megawatt in SPP, and then they shift all their load over there. So that would have a similar bad.
Yeah.
Certainly possible. Yeah, go ahead. Sorry, Luke.
I was gonna say, I mean, like, it definitely is possible. Like, I think they would, it'd be, you know, you would have a ramp rate requirement and just say, you know, for this sort of like controlled, like power shift sort of thing, it's like, yeah, you're gonna have to do something to ramp down power slowly, come back up, which they don't want to do that. These ALO facilities, that's well within the wheelhouse. It's not really a technical challenge there, mostly burning energy on the way up and down. But
That's one of those like complex behaviors that could be something as simple as a requirement to notify your system operator that you're going to do it and then ramp down at a rate that I agreed to. Right. So there's a lot of things for large load specifically, especially for what looks like ride through to the system that probably have really simple non-technical solutions that could be put in the regulatory space pretty quickly and agreed upon. Because that's like a no cost issue, right? That's a very simple solution. What the example was, the problem is that the folks who have the ability to make those decisions and put them into the requirements aren't talking to the folks who know what the large loads are going to do right now for a lot of reasons that maybe we won't go into all of them here, but there's a risk from the data center side that if they talk too much to the regulators, they're going to hurt themselves. There's a risk from the transmission side that if they make the data centers angry, they're not going to get customers. And all of those have the pressures of, winning the AI race in the US and all the other pressures as well. So there's a lot of reasons why the conversations aren't happening, which is going to probably end up more opportunity costs later. So it's really important to just have, and I've been saying this, that every time we talk large loads anywhere in any venue, to just, if you can have the conversation, and just have it in a safe space. And it's going to help everybody. And all it takes is, I think we have a lot more common ground between system needs and large load performances than we know about, right? And I think that the initial fear is that if I say I can only do this performance, that someone's going to say, well, you can't connect ever. But the answer could be, well, if you can't do that performance, how much could you do, for example, right? And that was a nice, easy collaborative discussion. You just have to have the talk, and that's really hard to do.
Great points. Thank you, Alex. All right, so we can look at, there's a few folks that have come up with requirements for large loads. One is American Transmission Company that was published in August of this year. And they've went with the blanket requirement to avoid studies and then individual requirements based on studies if you don't meet the blanket requirement. So that kind of option number 2 that we suggested earlier. And so they have an absolute variation magnitude of 25 megawatts over any 5-second period. And they have this voltage ride-through envelope that they are asking the loads to comply with. And there are some carve-outs in the requirement for if you can't meet it, basically we're going to study you and figure out what the impact is going to be. Don't exactly know how they're going to do that with the ride-through curves, but that is what they're saying. This is the actual language here. It's a little bit. This one is pretty clear. This criteria 1. This is basically that box shape. The second one here is any change in active power greater than 25 megawatts should be limited to less than 0.5 megawatts per second. So that's a pretty slow ramp rate, and it's I guess, yeah, it's there's been some interesting debate, I think, over this specific criteria. Actually, both of these criteria. And then one note there that it's highlighted here. So if these values are the total aggregate values for all sites at a given point of interconnection or at multiple sites, if oscillations are driven by common processes across sites. So at a given point of interconnection, even if there's multiple loads connected there, the total variation has to be within these bounds. And if you have 2 facilities or more facilities that are spread over some geographic area, if these oscillations are in phase from the facility, then the total amount of oscillation has to be within these bounds as well. So that's something that we've kind of heard about now and then, is that the large loads will tell us that facilities across the country even are going to be like synchronized very well for some reason. So all right, so we talked a lot about problems. Let's talk a little bit about fixes. So there's a few things. So some of this is come out of some papers that are public. This figure here is an example of something called a load floor and a controlled ramp here. This is something that I'm not saying that all the GPU vendors can do, but some of them have said that they can do this sort of thing. And what's happening here is that this kind of brown line here is the like we're calling it a load floor. So any of this GPU fluctuation that's happening below here, they're where the power drops below this line, they're doing a GPU burn basically at those during those interfills. So if they're filling all these gaps with basically burning power on the GPU, and by doing that, they are able to limit their total magnitude of fluctuation to whatever you see in the top here. They can't bring it all the way, to zero with this method for various reasons, but they can find something, whatever this is, maybe 80% or 90%. They can really take the bottom out of this variation. So that's something that seems to be available today. So this is all great in terms of like the total variation, but if in this band that's on top of the brown curve here, that might be where all the harmonic content is that you're worried about. So it may, depending on the machines nearby and the network connections and all that stuff, you might still have a significant problem even in this harmonic content that's just at the top here, or subharmonic, I should say. But this method can be used to really avoid a whole bunch of the fluctuation. The other one, like looking at at the GPU first, I guess, and then going out from there. But the other solution would be to use some sort of rack level energy storage that would be connected on the DC side of the power supply unit. So this is basically connect a battery or some sort of supercapacitor or something right on the at the rack right after the rectifier, basically right after the power supply unit. And then any sort of power fluctuations from the GPU can be sort of absorbed by that capacitor, and that capacitor or that battery will charge and discharge over time as it goes through these training cycles. And I think this is something that's been proposed a bunch of times, and I think this could be a really great way to handle this. And I don't really see why this wouldn't be the answer in the end. Have it just fixed right at the GPU before it's able to propagate anywhere out into the system. But again, this takes time for them to develop these products. Okay, there's a few more things we can do here. Now looking, beyond just the GPU and the power supply, we look at energy storage on the system, basically. So at medium voltage or at high voltage, we can use an eStatCom and possibly a grid forming battery to mitigate this as well. So like an eStatCom is a STATCOM that uses supercapacitors on the DC side. So it's got ability to store some amount of energy, and it's got a very high cycle lifetime. So it can do like a huge number of cycles before there would be any sort of lifetime impact on that supercapacitor. And the eStatCom, what they're kind of proposing would be to measure the load fluctuations and feed that fluctuation, feed that measurement into the controller, and then just offset it all the time so that you get sort of a balanced load profile at the when you look in from the wherever it's connected. So this is a measurement, typically a measurement-based solution here, and this is just, how effective it's going to be is just a matter of how fast the fluctuations are. Because it's measurement based, it there are time delays associated with the measurement, so it's not able to offset like, something at like, 200 hertz or something. Would be too fast of a fluctuation for it to be able to mitigate, but 10 hertz is definitely going to be in the bandwidth. 10 hertz and below. So, and they might be able to do partial mitigation. There's sort of a roll off in terms of how effective they're going to be as you increase your frequency. And they're, of course, downsides are that they're expensive and they would take a long time to get, that. Few other options would be a grid forming StatCom. So we know that grid forming's, sorry, not StatCom, just a grid forming battery. We know that grid forming is able to maintain transiently. It can maintain that inverter angle. So if you're able to put that constant angle very close to the load fluctuation, then that constant angle will absorb any fluctuation that hits it. It starts to be a matter of, how small can you get that impedance from the inverter terminals to the load. And, if you put it at low voltage in our tests, we've seen it be fairly effective. You might be able to also combine these two approaches inside of a grid forming battery. Some of the vendors are saying that we can do grid forming, and then in addition to that, we can also have a very fast load meter and feed that into our grid forming and make it be able to kind of do both of these things at the same time, which is seems like that would be very effective as well. And the fourth one here, so full conversion UPS with large energy storage or super caps. So this would be basically having probably at medium voltage, having a series of back-to-back UPSs basically, or just back-to-back inverter systems that just decouple the two systems from each other, and then all the fluctuations from the load get basically buffered by the DC bus of this back-to-back inverter system. And then when it comes out onto the grid side, you don't see any of these fluctuations anymore. So you basically are pushing all the load through a DC bus and using that to limit the fluctuations on the other side. Very effective. Might be maybe not expensive as some of the other ones, but it's going to be a fair amount of cost, and it's going to take a significant amount of time to procure. But it's, technically seems like a very feasible solution. And then the thyristor switched resistor. So this is one, I don't know, I don't think anyone is really proposing this, but in theory you could just have, but it's a measurement based thing. But anyways, you could have you just have something that, a big resistor there that just measures the load and just tries to compensate for it all the time, just by burning energy into the resistor. Not very environmentally friendly, but technically it could work, I think. And then the open question about potential software mitigation solutions. Can they do anything on the software process side of things to make this not be so synchronized across the plant? And there's been various proposals, but it seems like this is not sort of feasible right now because it would impede the efficiency of their training. That's not something they want to do. So yeah, that's it for large loads. It's a hard topic to let's say get everyone what they thought they wanted to hear out of large loads. But hopefully we got a little bit of a better understanding of the issues as we see them and some of the potential solutions and some of the ways you might frame some requirements around it. So to pause for questions.
So for the example, for large load, the VRT, or the voltage right through, So we consider time. For example, for this X seconds, and then stay online. Um, you know, for if it's more than that, come offline, or you. How about thinking of how much of you in adjusting your output instead of fully on, or fully off? Say if it's 1,000 megawatt load at bus, and then voltage is 9.9, and then I think it's gonna be 0.9 for X amount, X seconds, and then you come offline all the 1,000 megawatt, now it voltage is even higher then. So how about just thinking if there is a way to, they can do sort of calculation, how much of it need to be sort of shed so that the voltage at their bus goes to 1.
So use load tripping to recover the voltage.
Yeah, I mean, adding a dimension of like how much of you're gonna come offline instead of, you know, fully, they're very large data centers that if they come fully offline and then they would make a big swing, you know, maybe is it possible that we consider that into our curve that we coming up from a grid perspective?
So like I'm understanding like a staggered ride through. So like some of the load would trip at a certain voltage level, a different, some other at a different one, and then you could use some of that tripping to recover the voltage and then.
Yeah, like we have, maybe we have something like for a frequency, like 5%, another 5%, another 5% at different frequencies, or maybe do we have something for voltage like that?
I don't know. That's a good question. I don't know if that's been explored much, but
Yeah.
yeah.
It has, I mean, there's nothing like that for voltage right now, right? But that's one of the arguments for picking a minimum and asking for to maximize your ride through, because each manufacturer has a different ride through. If you don't, and you make sure you present it that way too, right? And that was a main problem with the original PR24 at NERC, was it was supposed to be at the beginning of that project a performance standard, which means you just ride. If this profile happens at your interconnection point, ride through. After like 7 years of standard development process for the original PR24, it basically got treated as a protection setting standard. So what happened was everyone just put their protection directly on the bounds of that curve, which means every site who did that has the same protection settings, which is the same problem you're kind of saying, is that then everyone trips off at the same event. Where if you have a minimum, that's a thoughtful minimum, and then you say just for the other manufacturers, don't artificially limit your ride-through capability, which I think is the words I used when we wrote it from NERC's side, was basically don't artificially limit or maximize ride-through capability without harming or degrading equipment, was the language we agreed on, with the minimum. Then everyone's different, and you shouldn't have one event everyone tripping off of the same exact disturbance. The other thing is that voltage is local, extremely local.
Yeah, I'm talking about what if they come offline enough that their voltage at their bus recovers to what it's supposed to be within the range. Then, you know, treating all the loads with all different amount and sizes with the same curve. Because the difference that a 1,000 megawatt data center if come offline makes in the impact is very different than a smaller load.
That's true, but if one, 10 megawatt loads is the same as 100 megawatt load, so like in the aggregate, those smaller plants still have an effect. So you should hold them all to a same minimum ride through and then let them maximize them there. That was kind of the same justification the FERC used when they said you have to register converter based resources below the regular NERC threshold, because they make a difference in the aggregate. right? So like, it could make sense to tier them and have hold bigger plants to higher standards. That's kind of what NERC does with their bulk electric system definition, right? Those connected at a, not dangerous, but a significant KV level at a significant size, which was 75 kV above 115 kV, or sorry, 75 megavars, MVA over 115 kV. That was what was determined to be big enough to worry about it. And now it's for those IVRs, I think it's 69 kV or 60 kV and 20 megavar MVA, I think. So there are good reasons to treat some differently than others, right? Because they could have a massive effect. Like, my opinion, offshore wind should have a super high threshold for reliability because they're massive and are usually interconnected to dangerous places or effective places. But it's hard to make that discussion, especially in the regulatory space, to say, because then you just incentivize everyone for building a big plant. Then everyone just builds a small plant. Like, I went through a bunch of IVR data through the alert process, and you'd be amazed how many exactly 74.9 megawatt IVRs there are out there. Because the NERC threshold is 75, right? But it can make sense, but I think just practically it's better to just say maximize it with a floor. You must do at least this, then we can plan for that. And if you ride through more, it's okay.
All right, so we got 22 minutes and um, so we got one more sort of like special studies category that we'll put out here. And it's an EMT course, so we'd be remiss if we didn't talk about lightning and TRV and capacitor switching and all that stuff at least a little bit. So I got a couple really short slides on it to give you all just a bit of a taste of it. We're not going to go into any of these in detail because we don't have time for it. But just so you guys, have an idea of what it, if you've never encountered this before. So these are what we're calling like traditional or classical EMT studies. These are really what EMT was originally designed to do, this and HVAC basically. It's to study these sorts of things. So TOVs, line design, installation coordination studies, where we're energizing lines, cables, transformers, shunt caps, etc. Faults and recovery, transient over voltages, and rating and performance studies. Lightning, TRV studies, transient recovery. There's a lot of good resources on these topics that are out there because we've been studying these things with EMT for like many years. I don't know, 50 years or something. Maybe not 50, but many years. So there's a lot of like kind of textbook type material out there, and a lot of the EMT tools have many good resources available online. PSCAD in their knowledge base has a lot of good content out there. So if you're interested in these things, beyond what I'm sharing here, there's a lot of places you could look. This specifically is I think it's from 2008. It's like a application guide for PSCAD basically. That was written a long time ago, but it's still pretty relevant, and I don't think the information's really gone stale in there. So this is a very mature area of study, I'd say. And there are more that we could talk about here. There's things like near miss or not near miss, zero miss studies. And a few other sort of like interesting things to study and talk about. But we don't have time for it today. But if you're definitely reach out if you have interest in this area. I'll put you in touch with the right guy in our shop. I'm not the classical studies guy in our shop, but I'll just say that up front. So we know that as time step goes down, we So, studying different phenomena, you need a different time step for. So steady state is, steady state, so infinite timeline, effectively. Long duration time domain analysis. This is basically like steady state, so very large time steps that you use there. Transient stability of performance. This is your, millisecond sort of, or larger quarter cycle type time step. EMT dynamic performance, kind of stuff that we talked about on day, yesterday specifically. Everything we talked about, we're using something in the, let's say, 5 microseconds to 20 microseconds in that range. And TOV and switching studies, these are now in that lower end of that, would say maybe like 5 to 10 sort of microsecond, or maybe a little bit lower in this, maybe in the single microsecond. And then way at the bottom, it's TRV and lightning studies, which we're using, single microsecond or even smaller for lightning. So our time steps get a lot smaller, and the way the models look changes a lot when we go to some of these very small time step scenarios. So this one, lightning studies, also called fast transient studies. What we're trying to do with these studies most of the time is to determine the impact that a lightning strike would have on a station or on a tower. And this assesses the shield wire configuration, the surge arresters, the insulation design, and figures out whether that design is going to be sufficient to avoid damage to equipment. And these are going to be very fast lightning surges, 50 to 100 milliseconds, 100 microseconds in duration. And we study these either as striking on the conductor itself or as striking the tower and then causing a voltage rise on the tower. So when we strike, we'll talk about the risks of those two scenarios. The strike on the conductor, you have a risk, you have a very fast voltage buildup on the conductor, and that you might have excessive voltage for the level of insulation that you have there. So you might have a flashover event where the fault basically flashes over the insulation, and you get sort of a fault happens from that lightning strike. So we want to avoid that if possible. And when we have a strike on a conductor, you have to imagine that it's, if you had shield wires, this lightning strike has somehow avoided those shield wires and struck the conductor directly. The other possibility is that it strikes the tower or strikes the shield wire, and we have a buildup of voltage on the tower itself, such that it actually is beyond the withstand capability of the insulators, and you have a flashover from the tower to the conductors. So both of those are not great situations, and we can try and design these systems to avoid that using a variety of methods. Some of the modeling details and assumptions here. So ultra small time step, we're talking potentially like nanosecond type time step for these studies. The lightning surge shape, these are pretty much defined in standards, I think, for the most part, of what sort of shape of that sort of current surge needs to look like for these studies. But there is still, a lot of debate over which shape and what's realistic and what isn't. For example, a strike on the tower is typically going to be a very much a higher current strike compared to the strike on the conductor, which that's just the way lightning works, basically. Can't do anything about it. And so yeah, surge shape makes a big difference for these types of studies. Stray capacitance starts to become a really big deal. So at these sort of like time steps and frequencies that we're looking at these systems in, any sort of like inductive element starts to look like a open circuit, basically. So your transformers, for example, you kind of model them as open circuits and just model the capacitances instead. we think of transformer, there's not a capacitor on the transformer, but there is some small capacitors on a transformer, which we call the stray capacitance. That's always there for any transformer or any breaker, any disconnect, any surge arrestor. All of these things are going to have some amount of stray capacitance. And when you're starting to look at these studies in a lot of detail, all of these things can really start to make a difference. And even like the station buswork needs to be modeled. Like even if you have line coming in on this side, line coming in on this side, and you can actually get detailed information about the station layout and the type of conductors or the type of the material that's used for the station, and all of those small station sections become frequency dependent lines in your study. So it's a very intricate modeling process. It's totally different from what we do for typical IBR interconnection studies. And this is what we have to do to figure out whether lightning is a problem. Grounding and shielding is, of course, is a very big deal. And, especially for the back flashover, if you have a lightning strike on a tower, if that tower isn't well grounded, then you'll have more resistance on that tower. And if you have a fixed current that you're pushing into that tower, then you'll have, for a not well grounded tower, you have a larger voltage rise on that tower, and then you might have a greater chance of flashover. So that becomes important as well. Steep front arrestor models is a thing as well. So an arrestor has a voltage versus current characteristic. It tries to clip the current at certain levels. And that profile that they typically give you is not necessarily sufficient for looking at very fast transients. What we often have to do is we have to take that current and voltage profile and split it up into a slower portion and a fast portion. We put a little filter in so that only the slow portions make its way through to the slower portion of it. So there's some intricacies there on arrestor modeling when it comes to these steep front transients. So we can run the study and figure out whether there's going to be a flashover event or a back flashover event for a given station. And then as a mitigation, we might use surge arresters, we might install better grounding, or we might use change the shield wire configuration, for example. It's also somewhat of a statistical study because lightning statistics, depending on where you are in the country or geographically, lightning may not be very, very often. So there's a bit of a statistical element to it as well. Next one I'll mention is transient recovery voltage studies. So these can be very interesting and somewhat complicated in a different way type studies. When you have a fault in a system and you want to clear that fault using your breakers, you open the breaker and there'll be a voltage buildup across the terminals of the breaker as you open that fault. And if that rate of rise of voltage is more than what the breaker can withstand, then you'll effectively have a restrike on that breaker and you won't be able to clear the fault. So this is, one guy in our shop is sort of the TRV guy, and he's got many years of experience doing these studies. And so we have some experience in terms of what, details need to be included for these sorts of studies in the general study process. Again, there's lots of resources you could look at for how to do these things. But there are, in terms of standards, there are fairly well-defined IEEE and IEC standards for how fast this voltage can recover, rise after the fault, and what's going to be a problem and what's not going to be a problem. And you have these sort of like profiles that look kind of like this for the rate of rise of a voltage, right? So if your TRV event that you're studying, if the voltage across the breaker rises faster than than the applicable curve from the standard, then you might have a problem. And these type of studies are typically done, they're typically triggered by some sort of change at the station. If there's a new line coming in, or if somebody is you know, thinking of replacing some breakers or something like that, then often these sort of like TRV studies are done to assess whether the equipment that's there is capable of handling the TRVs. Modeling considerations are, again, small time steps. These going to be sort of like 1 microsecond type territory. And there were very small models. It's going to be one station that's modeled in detail, and then the frequency dependent lines out of that station. And then the rest of the network is just a network equivalent. Again, we're doing really high frequency stuff. So, you know, inductors start to look like open circuit very quickly at those high frequencies. Straight capacitance and detailed buswork modeling can make a difference for these studies as well. And, you know, we'll do the study and then we'll figure out whether there's, you know, if it exceeds the criteria, let's say. What do we do next? Well, the first thing would be to check with the breaker manufacturer to figure out the actual TRV withstand capability. Often the actual capability is more than what the standard says. So you know, that would be one thing to do first before you decide, you know, you need to do, you know, replace a piece of equipment or something. So if it's still failing and the manufacturer says, yes, this is likely to be a problem, then a higher rated breaker may be needed, or some additional devices. You can use surge capacitors or grading capacitors to kind of absorb some of the issues related to this TRV can sort of absorb some of the voltage across that builds up across the capacitor. All right, so this is rapid fire. So next one, switching studies. This is like a whole huge basket of studies that I'm kind of lumping in with this. Probably not fair to include so many things in switching studies. And the classical study folks would be maybe not happy with me that said this, but line and transformer energization, faults, capacitor, or reactor switching, open line resonance, and a whole bunch of other stuff is kind of what I'm lumping in here with switching studies. So usually these studies are trying to figure out what the peak overvoltage is for these events in your system, and what is the peak energy that an arrestor that's in your simulation model is gonna measure for some of these events. And we want to verify whether the equipment overvoltage ratings are not exceeded, and to potentially check for problematic resonances that sort of coincide with some of these switching study problems. And there's textbooks of information you could look at that go through all the various sort of scenarios here. And a lot of this is like super interesting stuff. Just a couple notes on some of the modeling considerations. Usually we're looking at sort of what we'll say medium-sized models, so definitely bigger than Lightning and TRV models, but you might only need to look sort of 2 to 3 buses away, kind of depending on whether you're doing something where the system resonances at like 3rd and 5th harmonic, let's say, matter. So it'll be a little bit dependent on that, but you don't need, a massive system model to check a lot of these things. Time steps, again, a few microseconds to 50 microseconds is probably a bit high, but maybe in the 10s to 20s of microseconds. Some of these events are going to be very dependent on the point on wave at which you apply the switching event. So if you're energizing a transformer, for example, what we usually do is we'll do a statistical analysis where we'll switch the transformer in over a full cycle, and we will, one pole and then the other poles will close in with some variation around that first pole closing in, and we'll that'll give us sort of from a statistical sense, what is the worst case, energization transient, which we would see for a transformer or a transmission line, for example. And then another note on modeling, the nonlinear models are quite important for these types of studies. So the transformer saturations, the remnant flux, frequency dependent transmission lines, et cetera, are all going to play a big part in your results. And what do we do if something goes wrong? It's going to depend a lot on the specific issue that you see, but if it's a harmonic issue, maybe you'll use some sort of harmonic filter or something to shift the resonance away from the problem that you're seeing. If it's, let's say you're doing a transformer energization and you see that there is a high likelihood of having a problem with the transformer energization, then you can use like a pre-insertion resistor or, to sort of soften the switching is what we're kind of doing. We're adding damping into the switching by using a pre-insertion resistor. Or we can use point-on-wave breakers, which would have very good control over when exactly you're switching in that point-on-wave breaker to avoid a bad point-on-wave. So, yes, okay, that was fast, rapid fire, like I said. Some references in here. You'll get these slides later. You can read through these, and if you have questions, I can direct you to the right people. Right, some time. Questions on classical studies? Is there anyone that does classical studies, by the way? Yes. Okay. Fantastic.
Maybe just a question. The typical stray capacitance that we use for TRV, are those the same with the one that we use for fast front transients?
I would think so. Good question, but I would think so.
Because sometimes I'm looking cross-reference,
Yeah.
looking references from IEEE, CGRI, IEC, then the books from Greenwood, Greenham. They kind of suggest different values for different type of study.
Oh, really?
So I'm kind of confused which one to use. Although I understand what type of phenomena I'm studying, but by looking at the capacitance,
Yeah.
they sort of recommend different values.
No, it's interesting that they would come to different conclusions on that, but I guess it would just depend on what sort of testing they did to come up with the data that they recommended. But it's a really good question. I don't know. I don't, on the top of my head, I think you would, the stray capacitance is the stray capacitance. It's not going to change probably on the study type, but that's a good question.
Everybody done. All right, it's 2:30. Thank you for coming. Thanks again to the DOE for funding this opportunity. Thanks to TRE for letting us use the room. And as part of our thanks to TRE for letting us use the room, the faster we leave, the faster they can have their holiday party afterwards. So we'll just keep that in mind as we're packing